Hello, this video will show how to quickly build a boundary scan structural test with diagnostics for a populated printed circuit board using just boundary scan description language files and circuit trace. BSDL files define the implementation of boundary scan in individual logic chips and are available from chip vendors. Here is an image of the circuit board, which contains 4 boundary scan chips, JTAG chips, and this will be the target for our structural test. Here is the circuit trace's USB-based JTAG controller. It's called OnTap because it's used in our OnTap product. It has 2 JTAG channels, and channel A, port A, is connected via a Xilinx ribbon style cable to the target board. Flying leads connections are available, and they're more appropriate for general purpose connections. When Circuit Trace opens, you'll see a ribbon style menu plus the home screen and some docking panels. The controllers panel will have the focus, and that shows channels A and B. You can have any number of controllers connected depending on the number of JTAG chains you have in your project, or the number of GPIO pins that you might want to use. And this has a number of settings. For example, you can change the clock rate where you apply boundary scan. And so now to get started, what we will do is click up here on the system menu, and we're going to browse to a new project folder that contains our BSDL files. And so when we do that, this dialog opens. We will browse to that folder, select the folder. The BSDL files will now be shown in this list, and if we had a design netlist, we could optionally load that, and that would provide more context information throughout the project. So it's encouraged, if you have it, to use it. But we want to show this building this quick structural test using just BSDL files for now. So we'll go ahead, click OK. BSDL files now show up in this list, and we're going to build the project based on these. Now, we do have a board connected, the target board, and so we could use AutoDetect to automatically find and define our JTAG chain, but again, we want to show how to do this with just the BSDL files. So we will take these BSDL files and drag them over into the JTAG logics list, and I happen to know the order in which these should be. Here's the FPGA. Here's Xilinx FPGA. Now, if we wanted, we can drag and drop these into different orders. And the other thing that we can do is we can edit in place the reference designator so that the JTAG logic names match the reference designators on your target board. So we can edit in place, and this we know to be U4. This is called U3 on the target board, and U2, and U1. If we wanted multiple chains, or wanted to change the chain, JTAG chain designation, we could do it here. And you can have A, B, C, as many chains as you wish. So for now, we have defined the JTAG chain, so we can come up. Accept JTAG setup, click OK. And that will bring up the circuit docking panel and show in that panel the chain. I'll repeat that. There are quite a few settings here. I won't get into them, such as op codes that you might want to set, and any number of things. But for now, let's go ahead and build this project. So for that, we'll come up to trace connections, and we're going to trace through all pins. And what this means is that circuit trace will take each boundary scan output pin and transmit a signal from it, and then any other boundary scan inputs that receive that signal will become the basis of connections for our solution. So we will go ahead and do that. At first, let me turn off the power. The power is on our target board. I'm going to turn off the power just so you can see when that happens. You'll get a tap test fail, so check connections and power. So the tap test is done. Test access port test is done. So I'll turn it back on, and then we will try this again. And so now we're tracing through the circuit, pin to pin. And there are quite a few connections on the board. We don't have the net list, so circuit trace is just finding these connections. For example, we're showing a list of nets, and then here are the broadcast pins and detected pins. So pin R1 on component U1 broadcast a pattern, a test pattern, and it was received by R1 because it's an input-output pin, which makes sense as well, it passes. Pin P1, also on component U1, all received the same pattern, so it's asking us, do we want to connect it? We could do that, and we can go pin device by device, pin by pin, and do that. But let's say we want to check this connection. We click on the broadcast pin. That will bring R1 up over here. And now we can wiggle the pins high, wiggle that broadcast pin low, so it's transmitting, and you can see it's being received by P1. So it looks like a pretty good connection. So as I said, we can go pin by pin and do this, but we're going to take a shortcut here. Let's get our trace results back so we can see the reddish indicating that should action be taken, is something passing or failing. The green square with the checkbox says it makes sense and it's passing right now as far as circuit trace is concerned. So we're going to take a shortcut. We're going to go up to Learn Trace Nets, and we are going to click this. And so circuit trace has learned all of the connections that it just found. However, of course, the thing to be aware of is that we're transmitting signals throughout this board without regard to what constraint should be applied. We might be trying to transmit from a pin that controls power, or that might cause contention that enables memory devices, or that affects bidirectional controls, the direction control on such devices, buffers, transceivers, any number of things in the circuit. So we need to be careful about that. Now, driving from one pin at a time helps to control that a bit, but let's see how stable this is. We'll run the test again, and we see that there's one pin that's asking to be connected. So what we can do on that pin is put on an input off, output on, input off. Just turn off that input so it doesn't show, because we happen to know that that's not a good connection, and you may need to know something about your circuit to try that. So let's try this again. So now it's passing. Let's try one more time. And you might have to make a number of adjustments with guards. You can change the guards on these pins uh, depending on the application. So it appears to be repeatable, and at this point, we will insert a fault, which I can do by simply flipping a switch on the board, which will change the connection status, and then we will run all pins again. Okay, now I happen to know that the failure is showing up and it is connected to this pin. If you had the net list, it would probably show you the net name, and that would be more uh, context helpful. But so the failure is detected. That's a good thing. Let's turn the failure off, remove it, rerun the test. Okay, and now it's passing like it should. So we scan down through here, and we can see there are a number of connections that the test found. And it found a number of, it scans and looks for switching pins, pins where there are clocks, background clocks. It detects those, that's part of the test. Pull-ups, pull-downs, a number of conditions are actually checked on the board. And that net information, again, would be available if you had a net list. But the procedure would be the same to what we're doing. And if you want to refine the test, now that you have one, you can go over here, pick a device, view one here, get a list of pins, and then you can set constraints as you might wish. And again, that would be to control, directional control, say on transceivers. You might want to disable the pin on a memory device, the output's on a memory device that's connected to a scan pin. So those are things that can be done. You might say, well, I know a certain connection should be there. Let's see, U3 pin 8. Happen to know when, okay, that it's connected to a couple of other pins, and U3 pin 24 finds it. When it transmits, it finds U3 pin 8 under the list of detected pins, along with U3 pin 20, and that was also found. Something else that can be done for non-scan components on your board, you can use the script file, script capability, and what that is, it would, the script capability allows you to define pins and pin groups as variables, such as I'm showing in this text file, which would show up in the panel, by the way, if we had added it to the project. But it allows you to take pins and then pin groups and then manipulate them, drive them low, drive them high, put them in flow control statements such as force statements, and manipulate the circuit that way. So you can drive, sense, you can output messages. So it's a pretty powerful tool. So thank you for listening, and so long for now.